Finally, let's look at some more advanced examples. So in these examples, I want to find the Taylor series centered at x equals 0 for the given function. And just as a reminder, the goal is to try to figure out somewhere to start, and somewhere to start being one of our familiar functions where we know the Taylor series centered at 0, and then think how we can get from that familiar function to the one at hand and do those same operations on our starting Taylor series. And as is often the case, there are lots of correct paths that you might take to get to the end, and I'm just going to demonstrate kind of the way I might approach this. So here, there's several things going on. One of the things we talked about in the last video was that multiplying by powers of x is something we can certainly handle. So maybe my goal is to try to first figure out how I can express a power series for 1 over 1 minus x, quantity squared in the bottom, and then in the end just multiply by x squared. So that's kind of the process I have in mind here. So to think about 1 over 1 minus x quantity squared, the first thing that comes to mind is the power series or the Taylor series for the function 1 over 1 minus x. So I want to think about how I can get to this function from that one. And so your first thought might be that you could square 1 over 1 minus x, which is certainly true. But multiplication of series or squaring series is not one of the operations we talked about. And in particular, if I were to take the, so kind of red note here, if I were to take the square of a sum, that does not give me the sum of the terms squared, which might be our what we'd like to do. So a common mistake here is I see somebody taking the sum for 1 over 1 minus x and just squaring the terms. So the red is saying let's avoid that. But another way I can relate this function to 1 over 1 minus x is by observing that this is actually just the derivative of 1 over 1 minus x. This is preferable here because we know how to deal with differentiation with series. So in this case, I'm going to replace 1 over 1 minus x with its series representation. If you recall, that's just the sum of x to the k from k equals 0 to infinity. And then we want to just differentiate this. So the terms now become k x to the k minus 1. And this is an example where I actually want to change the starting index to 1. The reason is that if we were to write out these terms, the first term would be 1. If you take the derivative of 1, you're going to get 0. So the k equals 0 term here vanishes, and that means that we now start with the new first non-zero term, which was the k equals 1 term, and that's why we now change this to start at 1. So what I've ended up at the end here is a series representation of 1 over the quantity of 1 minus x squared. Once I have that, then to find the desired function, x squared over 1 minus x quantity squared, I'm going to take x squared times, in parentheses what I have on the top, I'm going to replace that with the series we just found, the sum from k equals 1 to infinity of k x to the k minus 1. So to be clear, this part is replacing what I had in parentheses up here. And then the last step is now I can bring in that x squared by changing the power of x from k minus 1 to k plus 1. I'm adding 2 to the exponent of x here. And so that is my Taylor series centered at 0 for x squared over 1 minus x quantity squared. I do want to point out that these are kind of shortcuts. So in finding the Taylor series, you could always use the definition, which requires that we find several derivatives of the function, evaluate them at the center, and try to come up with a pattern. However, if you tried to do that for this function, just finding the derivatives would become very complicated very quickly. So there's certainly more than just a shortcut. This kind of takes a problem that might seem unsolvable due to the complexity of the derivatives and makes it something that we can do without too much work at all. The next example we have here is x times arctangent of x squared. So of course the main thing that jumps out at me is the arctangent. So that's my starting point. I know a Taylor series for arctangent, and that has terms -1 to the k, x to the 2k plus 1 over 2k plus 1. Now, there's two things going on. There's function composition, and there's also multiplication. I'm going to do the function composition first, and as a general rule of thumb, I like to work my way from the inside out. And if I do this, I'm going to take my series from above and replace x with x squared. In doing that, again, I can now simplify this as -1 to the k, x to the 4k plus 2 divided by 2k plus 1. And this is the simplification step I mentioned before. The last step here is that I want to multiply by x, what I have above. So I'm going to take x times the series we ended up with in the above line. And this is where the simplification that we already did is very important, because what I should note here is that when I multiply by x, I'm just going to increase the power of x by 1. And this now makes my exponent on x simply 4k plus 3. So a few common mistakes that I've seen is, suppose I didn't simplify. And so if I didn't simplify, I'd be looking at what I'm circling in yellow here. It might be tempting to just say if I multiply by x, then I can just change the 2k plus 1 to 2k plus 2. But because you have x squared in there, you'd really be multiplying, but if you increase 2k plus 1 to 2k plus 2, you'd be adding 2 factors of x instead of just 1. So that would actually give us the wrong final answer. And by not simplifying, it's a very easy mistake to make. So that's kind of my reasoning for really saying, if you have a multi-step process, simplify as much as possible before moving on to the next one. And the other thing I'll point out here, suppose I first found the power series for x arctangent of x, and then my last step was to replace x with x squared. The only problem with that is that that would actually replace all of the x's with x squared, so you'd end up with a Taylor series for x squared times arctangent of x squared. Of course, you could then divide by x to get the right answer, but that adds an extra step. So that's, again, why I would like to first do function composition, and then always save that multiplication or division that might exist of powers of x for the very last step. And then I have one more example, the integral of e to the minus x squared. So note that this is one that this function is one I don't know an antiderivative for, but what we're asked to do here is essentially find a series representation for this antiderivative. So let me break it up into pieces. Of course, my eye is drawn to e to the x. So I want to start with my known Taylor series for e to the x. That has terms x to the k over k factorial. And then, again, think about this as working our way from the inside out. So my last thing I want to do is take the integral. Before I do that, I want to take advantage of function composition. So I can replace x in my series for e to the x. I can replace it with -x squared. Again, before I move on to that next step, I need to simplify this so it's very clear what my antiderivative is. So if I simplify this, there are a few things going on. There's a -1 raised to the k, and there's also an x to the 2k. So that's the way I can simplify that numerator. So my final step is then to take the antiderivative of the series I've found above. So I'm going to replace e to the minus x squared with its series representation. And note that I'm anti-differentiating with respect to x. So the only thing that should be affected by that is the x to the 2k. Consequently, my resulting sum still has the -1 to the k, and it still has the k factorial. But x to the 2k becomes x to the 2k plus 1 divided by 2k plus 1. And because it's an indefinite integral, I want to put the plus c in there. And just another kind of nudge towards simplification, a common mistake I might see here is if somebody, again, doesn't simplify and leaves this step here, And when you anti-differentiate, think, okay, I can just change the k to k plus 1 and divide by k plus 1. But of course, there's all kinds of problems with that. First of all, we need a 2k plus 1 in the denominator we see, not a k plus 1. That would make the exponent on x to the 2k plus 2, and it would also change the exponent on minus 1, which we said should not be affected at all when you differentiate with respect to x. So again, be very careful about these multi-step processes in terms of simplifying as much as possible within these separate steps.